I want you to meet Jocelyn. She's 21 years old and has a developmental delay and autism. She's a very limited vocabulary. I worked with her every day as a teacher's aide, and at the end of the summer, I was amazed when she was able to learn my name. I took a break from work to start my senior year of high school, and when I returned in November, Jocelyn was not responding to me, and she certainly wasn't saying my name. Her response got me thinking about the phenomenon of neuroplasticity. Neuroplasticity is the ability of our brain to form new connections and alter existing connections depending on what it is exposed to. Think words like synapse formation, axonal sprouting, dendritic remodeling, and even pruning. All these terms refer to growth, regrowth, and shaping in the brain. In the 1960s, Dr. Marion Diamond proved the mouse brain shrinks when exposed to an environment deprived of stimulation and grows in an enriched environment. And this happens regardless of age, so it wouldn't matter if you're 18 or 80. The idea was crazy because scientists had thought that nerve cells stopped growing after adulthood. But no, every part of the nerve cell from dendrite, soma, axon to synapse alters its dimensions in response to the environment. In animal models, this neurogenesis is known also to increase with exercise, learning, electrical stimulation, and certain medications. On the other hand, chronic stress, depression, and illness can reduce neurogenesis. We've seen amazing dendritic sprouting in crickets. The dendrite is the part of the neuron that takes in signals. When hearing is lost, by removing a cricket's ear on the right side, the dendrites from the nerve cell responsible for hearing on that side actually grow and sprout to the left side so that the cricket can hear again from both sides. There have also been remarkable examples of neuroplasticity in humans. People who have suffered from stroke losing the ability to walk underwent daily rehabilitation, moving on a treadmill suspended from a harness, and eventually they were able to take steps on their own. So is the same thing happening in humans that happened with the cricket? It's definitely not as simple as that, but some interesting discoveries have been made. It turns out that there are stem cells that line the fluid-filled spaces in the brain, or the subventricular zone, and they can be activated to become neural or glial cells, which are cells that act like a support or glue for neurons. They can actually migrate to other parts of the brain, especially the olfactory bulb, which is a sensory organ for smell. The ultimate role for these kinds of stem cells is not clear, but one element that is important to neuroplasticity is repetitive stimulation. When I think back to Jocelyn, it's that consistency that we lost. Understanding how to manipulate neuroplasticity and direct new growth of pathways could mean cures for many conditions in the future. In the meantime, I am back working every day after school, and I am back to exercising Jocelyn's neurons, and I am hopeful to get another glimpse of neuroplasticity right before my eyes.